Okay, hi everybody. We're going to go ahead and start looking at the test 3 review. And so I'm going to go ahead and jump through. What I've got here is the review. And I've also got a flow chart that will be attached to the exam when you take it. So we'll just kind of go through this. I just want to maybe help you see how things are grouped here. Okay, so I just want to take a quick second to talk about our little flow chart here. And just, the big idea is, first of all, what's the parameter? The parameter is either you're working with a proportion or a mean. Sometimes we don't use the word proportion. Sometimes we say percent or a rate, like an approval rate. These are all proportions or percentages. And means, I think are averages. Okay, so once you decide whether you're doing a proportion or a mean, then the question becomes whether you're doing one sample or two samples. Okay, so with proportions, with one sample, the very first hypothesis test we covered here was this one for a single population proportion. That was section 7.2. Okay. Then after that, we switched to means and one sample. And by the way, notice how the null hypothesis is on all of these. So P equals value. Keep on, that'll help, I hope. But anyway, when we did means with one sample, first we did when sigma was known, and then we did sigma unknown. They had the same null hypothesis and really similar test statistics, but one was Z and the other was T, depending on whether we knew sigma or not. Okay, so those sections were, when sigma was known, that was 7.3, and when sigma was unknown, that was 7.4. Okay, now after that, we switched to two sample stuff. We did the mean test for matched pair samples here. Next, that was in 7.5, and I am not going to be putting that on the exam. Okay, so I'm going to cross it out temporarily. Feel free to do that in your notes. 7.5 will not be on the exam. Okay, then we continued with two sample tests here. We did the proportions test first. This one was in 8.2. And then we did a means test with sample standard deviation, so it was a t-test. That was the last one, section 8.3. Okay, so those are the sections here for each of these. And just kind of just note that, again, 7.5 will not be on there. These don't follow the order of the book. They're just broken down with the flow chart. So best of luck with that. And these problems will go in the order of the book. So the first problem is going to be a 7.2 problem. Okay, so it says a magazine claims, let me get this going here. Magazine claims that more than 5% of U.S. passenger vehicles on the road are electric. You are skeptical and decide to investigate. So from a random sample of 850 cars, you find that 55 are electric, and you want to test the claim at 4% significance level. So the null hypothesis will do secondly. The alternative is the claim, and they are saying that it's more than 5% of U.S. passenger vehicles. This is about a proportion or a percent. Both of those start with the letter P. So P is greater than 5%. That's 0.05 is what they're claiming. The null hypothesis, of course, will be P equals 0.05. Okay, for a problem like this, where you're working with proportions, you're always going to need your sample proportion. But for the moment, let's go back and look at the flow chart here. Again, there's just one sample, 850 cars, 55 are electric, and it's about a percentage or a proportion here. So if you go back, the parameter is not the mean, but a proportion on this one. And it's a one sample problem. So here is the test statistic. I'll copy that over. And here's the requirement, NP and NQ both greater than or equal to 10, so you'll need to be checking that. Okay, so let's go ahead and get our numbers here. So with proportions, we always need a p hat value. P hat is always x over n. And it looks like we have 850 cars, and 55 are electric. Okay, and ignore the fact that the calculator on the left here says TI-30. This is the same as the TI-36, but it's a European model. Okay, so anyway, it's 55 divided by 850. So I get 0.647. I should do 3 significant digits, so we'll go with 0.0647. And yeah, that is 3 significant digits. We don't count leading zeros with that. So we've got our p hat. Let's go ahead and do our check here. Okay, so for NP, the N is the 850 there. And for P, you're getting that from the null hypothesis, 0.05. Okay, and so on the calculator, 850 times 0.05 is 42.5. That's obviously greater than or equal to 10. And while I'm at it, Q is 1 minus P. So Q will be 1 minus 0.05. And of course, that's going to be 0.95. Okay, so when we use that, we'll check NQ is 850 times 0.95 on the calculator. Oops. Okay, so that's 807.5, and it only needs to be bigger than 10. Okay, so we're ready to check off on our check. And then normally, after we get the null and alternative hypotheses and do the check, we generally would get our test statistic. So go and squeeze that in here. So the Z test statistic. So the formula, again, from the flow chart here, we're doing this one. Okay. Notice it had a null hypothesis here. So just to point that out, all of these have the null hypotheses in them. Okay, so we're doing this formula for our Z statistic. So P hat minus P over square root of PQ divided by N. All right, so the P hat value was 0.0647. P is 0.05. They are different. P hat's a little bigger than 5%. The claim is more than 5%. Okay, over square root of PQ, that would be 0.05 times 0.95 we got for Q. And then over our N, which was 850. Okay, so let's go over to the calculator. Okay, so that's going to be 1.966. I'll go 1.97. So that's almost 2 standard deviations, which generally we would consider statistically significant. Okay, now we need a critical value. We'll verify this though. So we need a critical value. So I'll just draw a little bell curve here. Okay, we have decided on this as a right tail test. Okay, so I'll just draw a little critical value on the right, like that. The alpha is 0.04, and it's one-tailed. This one's, the test statistic is a z-score. So the z statistics are in the bottom row of the critical value table. So again, it's 0.04, one tail, and it's a z-score. So I'm going, nope, different document, hang on. So, see if I can pull this off. There we go. All right, so here's the table. Yeah, table A2. I think we agreed on a 0.04 one tail. So here's 0.04 one tail all the way to the bottom row down here. And I think I see a 1.751 there. Okay, so let's go back. This may be too hard. There we go. What did I say? 1.751? Okay, that's our Z critical value. And that's from table A2. I'll make the note here. All critical values come from table A2, Z and T. Okay, and then just notice the 1.97 is out in that right tail. So I'll just put a little dot over here to indicate that's my test statistic. So that indicates statistical significance, and whenever we have statistical significance, we end up supporting the alternative hypothesis. Okay, and then back to this, we want to get a p-value. Oops, sorry. So once again, we need a little bell curve diagram. I'll put it over here. Okay. This time we're going to plot, uh-oh, something went wrong. Okay, so this time we're going to plot the Z test statistic, 1.97. Okay, and the tail, it's a right tail test, so we need that. This will be our p-value. And as you know, the table only gives left areas. We need the right area, so we'll do 1 minus whatever the table gives. Okay, and we're going to go to table A2 for this. Sorry, I apologize, table A1. So once again, see if I can do this. Very good. There we go. Table A1. I think it was 1.97 for our test statistic. So I'll zoom in. Okay, so 1.9 and 0.07 gives 0.9756. Okay, so let's zip back over here. 9756. Remember, that's the area to the left. P-value on a right tail test is the complement of that. Like that. So it's 0.0244. So 1 minus 0.9756 is 0.0244. Okay, so the p-value is a 0.02. And 0.02 is definitely less than alpha, which was 0.04. Okay. So less means, oops, sorry. Okay, so less, that means we're going to reject the null hypothesis. we're going to support H1, which had said that P is bigger than 5%, P greater than 0.05. Okay, so that was the proportion of cars on the road that are electric. We have evidence now, so we can say it. The data support the claim. Okay, so more than 5% of cars on the road. Let me clean that up a little, make some space. Are electric. Like that. Okay, hey everybody. So now we're going to jump into question 2. So this one, let's go ahead and read it, and then we'll try and figure out what kind of problem it is. So for a given computer component, the manufacturer claims that the mean time, there's the word mean, so we're going to do something on means on this one. The mean time between failures is 837 hours. That's a claim. It's not based on data. A modification is made which is supposed to increase the reliability by increasing the time between failures. Tests on 34 modified components. Let's go ahead and make that note. N is 34. Produce a mean time between failures of 860 hours. That's a sample mean. Okay. The population standard deviation right here is believed to be 57 hours. So we'll call that sigma is 57. It says test the claim the modifying component's mean time between failures is greater than 837 hours. So that's an alternative hypothesis, that the mean is greater than 837. Okay, the null hypothesis would just change that to an equal sign, that mu is equal to 837, like that. Okay, so let's go back, and it gives a 5% level of significance. Let's make a note of that. So our alpha is 0.05. Let's take a second to just find this on the flowchart. So we'll slide on up here. The word mean comes up repeatedly. So under which parameter here, we're going to look at means. There was only one sample, and the question is the population standard deviation known, or is it unknown? Well, it clearly gave a population standard deviation, right here, population standard deviation of 57. So the standard deviation's known. So again, it's a mean, one sample, sigma is known. All right, so we're going to put in this test statistic and note that the sample size needs to be bigger than 30, or the population has to be normal. And I think the sample size was bigger than 30. So I'm going to go ahead and copy this statistic over and do a real quick check off on my sample size. This is bigger than 30, so we'll check that. Okay, and then the z-test statistic is x bar minus mu over sigma divided by the square root of n. Okay, so and we've got all these numbers. So the x bar was 860 minus the mean time between failures, which was 837. Okay, one's the sample mean, the other's population mean. Over sigma, that's 57, divided by the square root of n, that would be the square root of 34. Okay, so let's see what we get there. All right, 860 minus 837 over fraction 57 divided by square square root of 34. I'm going to put a decimal point there so that it comes out in decimal. And 2 places is fine on z-scores. We'll go with 2.35. Okay. We could get a critical value now. Okay, so this is a z-statistic again. And 0.05, it's a right tail test. I'll go ahead and make that note here. This is a right tail test. Okay, so on the right, we'll put z critical value here. Our alpha is 0.05, and all the critical values come from table A2. So I'm going to slide over and see if I can pull this off. All right, so table A2. Okay, so in this one, as we said, it's a 5% level of significance with a right tail test. So one tail alpha 0.05, z-scores are always in the bottom row. So if you can see that, that's a 1.645 down there, okay, for our z-score. And so I think I'll put that in here, 1.645. And then our test statistic is way up higher than that, so that's good news. We'll be able to support the alternative hypothesis. So that's our z test stat of 2.35. Okay, and so that's significant. Okay, and then next we want to do the p-value. So I think we'll do another little bell curve here, and this time we'll go out a little further into the tail for our test statistic, 2.35. Okay, the area of the tail here is the p-value now. That's a right tail, so we're going to have to do a complement on this. So we'll do 1 minus whatever we look up. When well, what we get when we look up the 2.35 z-score. This is a z-score. All the z-scores are on table A1. So let's slide over to that table real quick. We're looking up 2.35 on table A1. So here's 2.3, here's 0.05, and it looks like we're going to do the 9906 here. Okay, so we'll put in a 9906 as the area to the left. P-value is the complement of that in the right. So let's see here. 1 minus 0.9906, 0094. There. So then, of course, that's well under 5%. So the p-val is 0.00. Just focus on those first 2 digits when you say that 0.00 is less than 0.05, which was our alpha. Less means reject the null hypothesis, and will support H1, my apologies. H1 had said that the mean is greater than 837. Okay, and then we'll squeeze in a little conclusion up above here. So the data support the claim that the mean time between failures is more than 837. $837 hours. Okay, and that's it. Okay, so we're going to go ahead and start this next problem here. So let's go ahead and just make some notes on what it says. First, an article in Wikipedia claims the mean body temperature of adults is less than 98.6 degrees Fahrenheit. So that's an alternative hypothesis that mu is less than 98.6 degrees Fahrenheit. So the null hypothesis would just say that it's equal to that. Okay. This goes against everything, absolutely everything you've ever been taught. So you gather 565, okay, N is 565 healthy adults and observe a mean body temperature of X bar equals 98.2 with a sample standard deviation of 2.6, a sample standard deviation. That's S, not sigma. Okay, so sigma is unknown, but S is 2.6. Test the article's claim at a 5% level of significance. So our alpha is going to be 0.05, and the article's claim is just this one, that the mean body temperature is less than 98.6. So again, is a claim about a mean, okay, and the population standard deviation is unknown. We're using a sample standard deviation. And there's just one sample that's reported here. So let's go up to the flow chart. Okay, it's about a mean. There's only one sample's worth of data, and this time sigma is unknown. So we're doing this t-test statistic here, and the degree. And it requires n greater than 30, or the population is normal, and then the degrees of freedom are going to be n minus 1 when we look this up. So I'm going to copy this t statistic over. Okay, so I think I can do it, squeeze it in down here. So our test stat is X bar minus mu over S divided by the square root of n. So the X bar 98.2 minus the mean, which we're assuming is 98.6, okay, over sample standard deviation of 2.6 over the square root of n. That would be the square root of 565. Okay, so I think we'll go ahead and do this computation here. Fraction 98.2 minus 98.6 over fraction 2.6 over square root of 565. Okay, so there we're getting negative 3.657, I guess. There. All right, so we're good with our test statistic. That's quite big. It seems to be highly significant. Now, for the degrees of freedom here, we're going to have to just deal with that, but we'll look at the table first and decide what we're going to do. for the critical value, we'll look at table. Let's just actually paste in a little image here. And for the critical value, this is a left tail test. So right here, we'll have our T critical value. It's going to be negative. Okay. And so the sample size is 565. The degrees of freedom technically are 564, but you're not going to see that on the table. So let's see what we're stuck with here. Oops. Table's not there. So my table I'm going to have to slide over to. Okay, we're looking for a critical value, and I don't have 564 degrees of freedom, but I do have 500. All right, so with 500 degrees of freedom, that's the closest we can get. We, I think, are going to go over to 1.648, which lines up with an alpha of 0.05 in one tail. Okay, 1.648 there. Making it negative. This is table A2. And the degrees of freedom used. Let's see, just the degrees of freedom is 564, but we used 500. Okay, and so there we go. You can easily see that our test statistic is in the tail. Okay, so that makes it significant. All right, and then we want to get a p-value next. Okay, and so here we're going to have to put our negative 3.5657. So that's our T test statistic here, okay? And the area to the left of it, I'll shade in blue, that's going to be our p-value. So this is our p-val. Okay, and so I think we'll call that 3.7. I'll go ahead and diagram this one. So we're looking at table A3, which has the T distribution p-values. So for the degrees of freedom, I don't know exactly what we're going to use. We'll probably have to use infinity. The T test statistic going down is negative. I guess we'll go negative 3.7. Okay, just rounding this one over. Okay, and so let's just jump over to the table. Okay, so as I said, we want to do negative 3.7 on the test statistic, but then for the degrees of freedom, you can do 100 or infinity. I think I'm going to go with infinity. Technically, that's a z distribution. Let me just slide this on down here. And I think we've identified that we're going to go with 0.0001 as the area in the tail here. And so, yeah, that'll be our p-value. This is a left tail test, and these tables just give left tails. So 0.0001 is what we'll use. So again, what we want for the degrees of freedom is 564. So that's what we would look for, right? 564. Okay, but we're using infinity. Okay, and again, that gave us a point .0001. That's the area to the left. This is, let's make the note here, a left tail test. Okay, so we don't have to do anything to the p-value here. That'll just be .0001. And so we're almost done. We can just say the p-val is 0.00, which is less than 0.05, and that's our alpha. Which means, yes, less means that we reject HO. Support H1, which had said that the mean is less than 98.6 degrees Fahrenheit. Okay, and then we'll just try and put that into words. We support, the data support the claim. That the mean body temperature, oh, I wrote the wrong word there. The claim that the mean body temperature of adults is less than, I need a little bit of space here, so I'm going to squish this just a bit, less than 98.6 degrees Fahrenheit. Okay, so we're going to do a couple more here. Just to let you know, this question for this one is 7.5 material. And look, I just did it. I have decided that I don't think I want to put 7.5 on the exam. Okay, so I've got it here, and just for completeness, that's 7.5. I'm not going to test you on it, so I just thought I'd let you know. I don't want you guys to get overwhelmed with too many of the same kind of tests. Okay, and so then we're going to jump up to to problem number 5, and I guess I should have said what these problems belong to. So this first problem, I believe, is a 7.2 problem. Okay, the second one is 7.3 problem. Third one, 7.4. Fourth one, 7.5, as I already mentioned. So the fifth one is going to be 8.2. Okay, and the next one will be 8.3, just FYI. In case you want to go back and look at those. Okay, so let's get going on this next problem, number 5. I think we'll just go ahead and read this. It says, it's well documented that even with the same level of experience, women make less money on average than men for the same work. In some U.S. cities, women do better. A newspaper article claims that in San Francisco, a higher percentage of women earns 6 figures or more. Okay, that's a claim about a percentage, notice, and percentage is just another word for proportion. Higher percentage than men, maybe? It says a random sample of 400 women in San Francisco had 12 who earned at least $100,000, that's 6 figures, while a random sample of 700 men had 10 who earned at least $100,000 a year. So then it says to test the claim at 2% significance. So I think I'd like to get the sense of what the claim is. So just real quickly, it does talk about a higher percentage of women, and it's obviously comparing it to men. And so this is a claim about a percentage. There's two groups, the women and the men, two samples. So if we slide up to the flow chart here, again, this is about proportions or percentages, same thing. Okay, there's two groups, the men and the women, and then this is our test statistic. You can also see the null hypothesis here is P1 equals P2. There's some other numbers here. We'll need the P bar and the Q bar, and then the requirement for this test is at least 10 successes and failures in each sample. So that's the gist of it. Again, this is section 8.2. So let's go back to the problem. Okay. So I think what it said was that the null hypothesis, let's go ahead and get this down. The null hypothesis is that the two population proportions, this is for women and men, that those proportions are equal. The alternative hypothesis is, it's a little weird, but they're talking about the women. So it says that the women, a larger proportion or percentage, where is it right here, a higher percentage of women. So the proportion is higher for women that earn 6 figures or more than the proportion for men. Okay. I think probably be worthwhile doing our data. So let's separate the women and the men. Okay, and so for the women, it looks like we had 400 women. Let's see, right here, 400 women and 12 who earned 6 figures. So your N1 for the women is 400, and X is the number of successes. X1 was 12. Okay, and then we'll need a P hat 1. That'll be X1 over N1. So 12 divided by 400. Oops. Let's see what that is over here. Trying to get my calculator going. Okay, so 12 divided by 400. I bet you it's a nice round number, 0.03. And, you know, you could do 0.03 or 0.0300. That's 3 significant figures like that. And then let's do the men. Oh, while we're at it, we noted that we needed to count successes and failures. So for the successes on the women, there were 12. And that's greater than or equal to 10. So we're okay there. And for the women, the fails is a little harder. You're going to have to do 400 minus 12. Okay, which that'll be 388, I think. Which, of course, is also greater than or equal to 10. So we're good to go with the successes and failures for the women. Obviously, we'll need to do that for the men as well. Okay, so let's go on here, and I'll do just another section for men. Okay, so the sample size, N2, it says that there were 700 men right here and 10 who earned 6 figures or more. So N2 is 700. Okay, the number that earned 6 figures, that's the number of successes, just 10. Okay, and then we'll do our P2 hat. Here, obviously, that's going to be X2 over N2. Okay, so 10 over 700. The 10 divided by 700. And that comes to be 0.0143. Okay, so that's that. Looks good. And then we want to focus on successes and failures. So with the men, the successes looks like there's 10 men, which is big enough. You just need at least 10, which we've got. And for the fails, we had 700 people minus 10 successes. So obviously that's 690, which is also greater than or equal to 10. And so we've earned our little green check mark here as well. And then the only thing I think I would add down here is work on the P bar and the Q bar. So I think I'll put that down below. Okay, so real quick, the formula for P bar is x1 plus x2 over n1 plus n2. Okay, so just adding up the total successes, there were 12 for the women and 10 for the men over, let's see, 400 and 700. Okay, so we'll double check that real quick. So 12 plus, so you know what, I should have made that a fraction. So 12 plus 10 on top. 400 plus 700. I'll put a decimal point there so it comes in decimal, and it's beautiful. It's just 0.02, real simple. And then don't forget Q bar is 1 minus P bar. Okay, so 1 minus 0.02 is the complement of 2%, which is 98%. Okay, so that's pretty straightforward. Now I've got the formula for the test statistic up here that I just put up a minute ago, so I think I'll go ahead and just kind of nest this over a little further, and I think I'm going to try and put some boundaries up here. All right, so for the test statistic, we're going to go ahead and do our p hat 1, which is 0.0300. I'll just write 03 here. Then minus the p hat 2, that's the 0.0143. And then minus the 0, which has no bearing on the answer. And then over the nasty square root here, okay, so it's going to be 0.0, it's P bar Q bar, so 0.02 times 0.98, and then we just divide by the sample sizes. So first sample size is 400, and then same numerator, so 0.02 times 0.98 over 700. Okay. Oops. I'll just shrink that down just a bit. Looks good. And then fish my radical bar here. Like that. Not very pretty. And so then we can go ahead and evaluate this. So the fraction on top, 0.03. Nope, that's not right. 03 minus 0.0143 over square root and a fraction 0.02 times 0.98 over 400. Next, we want to add in another fraction, same numerator, 0.02 times 0.98, and this will be over 700. Okay, so that's the 1.79, I think is how we'll round that off. Okay, so let me get that here, approximately 1.79. Okay, and then the next thing is we'll need our critical value and then a p-value. So, so for the z critical value, we would go to table A2 on this. Our alpha up here is 2%. You can see right here. Okay, so we'll just ignore degrees of freedom. These are z-scores, so we go to the bottom row where it says large, z. Again, it's 2% for our alpha, and it should be a one-tailed test because of P1 greater than P2 there. So we'll just put one tail down here. Okay, and so I don't know what that is. Let's just slide on down to that table. So two-tailed point, what? 0.02. One-tailed, sorry. Okay, so one tail, 0.02, right here, all the way to the bottom. So way down there, you'll see the 2.054. So that's our test statistic. So let's put that in here. Okay, and then I'll just sketch in a little bell curve. I'm actually going to steal the bell curve from the previous page. Looks pretty good to me. Oh, except for this is Z, so I don't want to copy that T. Okay, so here's my little curve. Okay, and right tail, right? And I guess I could have written that down here, that this is a right tail test. Okay, so we'll put this on the right tail, 2.054 right here. Okay, the area of the tail is alpha. So 0.02. Okay, and then you might just note that the test statistic here, this 1.79 is not in the tail. It's a little short of that. So I'll go ahead and just note that, that this is your test statistic. It's not in the tail. The 2.054 is the Z critical value. Okay, so there we go. This is we would conclude that this Z test statistic is not statistically significant. Okay, so the next thing is we're going to need a p-value. So here we go. All right, so we're going to go to the probability table for the normal distribution, which is table A1. And we're going to look up our test statistic, which was 1.79. So we go down to 1.7 and then 0.09, like that. And that'll tell us the area to the left of our test statistics. So let me just kind of set this up here. Okay, so here's our curve. It's a right-tailed test, so we're interested in this area. And actually, I'm going to push that a little further to the left because we know this is not going to go into the tail. So here, that's the 1.79, which is our Z test statistic. Okay, and then the area of that tail will be the p-value. Okay, so I think we can now determine what that is. So let's just real quick here, p-val. Okay, so 1.79, this is table A1. Here we go. So 1.7 right there. And then 0.09 way over there. Okay. And so it looks to me like a 0.9633 is what we want. Okay, so I think we can just go ahead and put that in here. Okay, and that's the area to the left of the test statistic, 9633 there. That is not the p-value. We need the complement of that. So we're going to do 1 minus 0.9633 there, which is, I have no idea, 1 minus 0.9633 is 0.0367. Okay, so that looks good. And I think we're ready to wrap this thing up. So okay, so our p-val is 0.03, and then I'll obscure the 6.7. The point is that the 0.03 is bigger than alpha, which was 0.02. And it's greater, it's not less, okay? So not less means that we are going to fail to reject the null hypothesis. And don't support H1. H1 was the claim that had said P1 is bigger than P2 here. So that was the proportion of women who earn 6 figures or more in San Francisco. The claim was that there was a higher proportion or a higher percentage. The data do not support that. It doesn't mean it's not true, but we just don't have evidence here that kind of demonstrates this. Okay, so let's go ahead and write our little conclusion here. The data do not support the claim. That a larger proportion of women in San Francisco earn 6 figures or more compared to men. Okay, so that's that one. Okay, I think I could have centered that whole thing a little better, but that's okay. Okay, everybody, so we got one more problem to work here. This is problem number 6. Probably we want to just go ahead and read through it first. So it says, you believe the mean age of Republican voters is greater than the mean age of Democratic voters. To prove your belief, you sample 127 Republican voters, and you get a mean age of 52 years with a sample standard deviation of 17 years. Okay, from another sample of 185 Democratic voters, the mean age is 48 years with a sample standard deviation of 21 years. Test the claim at 1% significance. Okay, and it says that there's 301 degrees of freedom on this one, so that's nice to not have to compute that. Okay, so I think we should just kind of note what it says here. You believe that the mean age of Republicans is greater than the mean age of Democrats. So you're looking at means here, and there's clearly two groups. So let's look at the flow chart again real quick here. So it's not about proportions. This one's about means, and we have two groups, okay? So the question is it a matched pairs test? No, we're not going to do 7.5 on the exam, okay? This one's going to be the one with independent samples, two completely different groups of people, and this is sections. That is not correct. It is not 7.6. So let me fix that real quick here. Okay, so this should be section 8.3 for this one. Okay, so we'll go ahead and just remember the null hypothesis on this one. Right here is that mu1 equals mu2. Okay, so here we've got our test statistic. And the requirement here is your sample sizes should be both bigger than 30 or the population should be normal. And as it says here, I'll be providing the degrees of freedom for this one. Okay, so again, there's our null hypothesis. I think we go ahead and put this down here. Okay, so straight away, I'll go ahead and do the hypotheses. Null hypothesis is that mu1 equals mu2. Okay, mu1 is for the Republicans. H1, you believe the Republicans have a higher average age, so your belief is that mu1 is greater than mu2. Okay. Now, for the data, we'll list Republicans first. Okay. So your sample mean, it says you had well, I put in this, all three here, S1, X bar 1, S1, and N1. Okay, so what I see first in the problem is 127 Republican voters. The mean is 52, and the standard deviation is 17. Okay, so 127 for the sample size. The mean is 52. Okay, so it says the sample standard deviation for the Republicans was 17. And the sample size is 127. Okay, that's bigger than 30, so I'll go ahead and denote that here. And then for the Democrats, just a quick scan here. 185 of them, the mean age is 48 and the standard deviation is 21. Okay, so our X bar 2, 48, standard deviation S2, 21, and N2, the number of them was 185. And yes, this is also bigger than 30, so we can check that. Well, the last thing I think I would add here is the level of significance is given right here, 1%. So let's put that down, 0.01 for our alpha. Okay. Now, I have taken the liberty to copy the formula down for the test statistic here. So let's just take a moment and key that in. So it's X bar 1, which is 52, minus X bar 2, which is 48, and minus the mean difference we assume to be 0 because the null hypothesis says the means are equal. So when you subtract them, you'll get 0 over, now our square root. We'll have S1 squared, that's 17 squared, over N1, which was 127, plus S2 squared, that's 21 squared, over N2, which is 185. Okay, and then we'll just do that on the calculator. Oops. Okay, so fraction, 52 minus 48, and I don't need to say minus 0, but there it is. Square root, fraction 17 squared over 127. Okay, to the right, plus fraction, 21 squared over 185. Put a decimal point so that I know it will come out in decimal. And so here I got 1.8853, I guess. So we're good to go there. All right, so next we'll need a critical value and a p-value. We're coming along here. So I think I'll just wall that out and work on the critical value next. So a little picture of a bell curve maybe down here. Over there maybe? I'm gonna make it bigger. Too small. There we go. Okay, so now we're doing the critical value. This will be table, critical values are table A2. The degrees of freedom for this test, it says here, are 301. So we're not going to be able to find a 301 here. We'll go down to find something close, but I'll just go ahead and put the 301 here. Okay, and we'll just find the closest thing we can to that. And then our alpha is 0.01, and this is, let's go ahead and note here, this is a right tail test. Okay, so yeah, alpha is a 0.01, and it's one tail. Okay, and so, yeah, we're going to have to sort of approximate this, but let's see what we get. It'll be close enough. So all the tables are down at the bottom. 301, 0.01, one tail. Here we go. Notice there's a 250. That's pretty close to 300. And 0.01, one tail right here. Okay. So we're getting that. 2.341 is what we'll go with. Okay, and I think I'll just clean all that up that I just drew. All right. What was it? 2.341? Yeah. Okay, so I'll put that down here. 2.341, and then I'll go ahead and whisper what I actually did. We used 250 here. And then I'll just remind you, you won't have to do that on the exam. The degrees of freedom will be on the table. You won't have to, come to the closest one. Anyway, that's a 2.341. That's what we're considering statistically significant. So I'll put this down right here. 2.341. That's our T critical value. Okay. The area of the tail past the critical value is always alpha. So let's put a little alpha here. Ooh. Okay, a little alpha of 0.01. The test statistic 1.853 is not landing in the tail. It's right here. So that is my T test statistic, and it's not significant. Okay, so I think we're good here. Then I'll do the p-value. I don't know why that's also spread out. Let me pull this a little bit closer. Just make it look a little less lonely. Right, and it's a little more cleanup. I'm just trying to squeeze things together here. So then let me go ahead, and we have to still do that p-value. Okay, and for the p-value, we're going to have to do, this is a t-distribution. So the t-distribution p-values are table A3. Okay, and you may remember table A3 is a little different because the degrees of freedom go across the top row. We are told that there's 301 degrees of freedom, and that our test statistic here is, so up here is 1.853, and we're going to have to round that. We better go to 1.9 1.9. Remember, this only does one place after the decimal. So 1.9 there. Okay, and so then you're not going to have a 301 degrees of freedom either. So let's do our best, but again, table A3 way down here, this horrible one. Okay, so there's 100 degrees of freedom and there's infinity. And to be honest with you, I don't know what's better. So I'm going to go with 100 degrees of freedom. I'll go ahead and write that down. So I'm going to do 100, even though it's 301. And I think we said the test statistic was 1.9. So through 100 degrees of freedom, and I'm going down to 1.9. Okay, and we'll just go all the way down here. Okay, and I believe it's this entry. It's not going to be that different from the other one that's right next to it. So this is 9698. On the right is 9713. It's kind of, they're both about 97%, but anyway, we went with the 9698 just because we had to pick one. That will not happen on the exam. Okay, so 0.9698 is sort of the area we're working with here. And so I'll make the note here that came out to be 0.9698, but that is not the p-value. Remember, this is, I'm going to denote a t over here. So this is a right-tailed test. Okay. So let me put this here. The test statistic here. It was 1.853. That's our T test statistic. Okay, and of course we rounded that to a 1.9 in the table. And so the table is telling us that the area to the left is 0.9698. Okay, so here's the p-value. So the p-val will be 1 minus 0.9698. I don't know what that is, so 1 minus 0.9698. That did not work. 9698. So it's 0.0302. Okay, and that's bigger than 1%. The alpha was 1%. Okay, so now we can kind of start to wrap this thing up. Our p-val was 0.03. I'll be sort of ignoring the 0.02. So 0.03 is greater than or equal to 0.01. That's our alpha. It's not less. Okay, so what that means is we're going to fail to reject the null hypothesis. And we don't support H1. H1 had said that mu1 is bigger than mu2. Okay. And now I'm going to try and squeeze a little conclusion down here that it's about the mean age of Republican voters being greater than for Democrats. So that's what's being claimed here, and we can't support that. Okay, so the data don't support the claim. That the mean age of Republicans, I'll just say Republican voters, I think is what it said. Yeah, voters. Is greater I'll just say than for Democrats. And I'll abbreviate that too and show, just to keep a little space left there, so it's greater than for Democrats. And that's it. Best of luck to everybody.